Okay, so what I'm trying to describe here is the arc, what the arc length is, arc length, and how that influences the distance to horizon. So if you look over in this diagram, I've got these dotted lines that come up. Each of these dotted lines represents about 15 degrees. Actually, it is 15 degrees along this 90-degree arc here, with a radius of 3,959 miles, and each arc length of 90 degrees is a quarter of that of the circumference, which ends up being 6,225 miles. So, and what I'm showing here is the length, the distance to horizon, which is calculated, as I said earlier, by this value here, which is 1 of the cosine of the angle, divided by radius minus radius. Again, it's just calculating this value here. And as the object, and in this case I was talking about a boat, travels down the curvature here, and imagine a line, imaginary line passing through the center of the boat, and this line is an extension of the mast, getting to the line of sight of the person at this location here. So this is the important part here, is that the person here, for the purposes of describing what we're calling a curvature, is fixed. So the person is fixed here all the time, and you have an object slowly moving down the ball, right, until it gets to that point. And then what is the required height, right, that would be required for the person at this location to see the top of the mast? That to me is what we're trying to figure out here, is that when people are calling it drop, they're calling it curvature, calling it whatever. What I think we should call it is something I call effective curvature, or the effect of the curvature. So if we were on a ball, this is the experience we'd have, and these are the distances that would be required for the top of the mast be visible to this person at A here. So they're looking like basically right along their line of sight, and that's the distance that that object had to be. And then here, this is the distance it had to be at, this is at 60 degrees, here's 45 degrees, 30 degrees, 15 degrees, and smaller, 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 smaller. So that's what these columns are describing here. So this is the actual distance to horizon, and this is the degree. So this column here is the actual degrees away from the axis, if that makes sense. So these are the actual degrees. So a fraction of a degree, 1.44 degrees, which ends up being like 100 miles, right? So at 100 miles, using the calculation I have, it's 1.26 miles is the distance to the horizon. So that would be 100 miles there. And if you look here, the curvature calculation is very close. They're very similar. So they're pretty much effectively the same thing up until a certain point. And if you notice, at around 2 degrees here, to almost 3 degrees, it starts diverging. The numbers, if you look, that's very similar. So the numbers actually start diverging more rapidly as you go up in, let's see, look here, 3 degrees, the values are a little bit different. And then as you get to 49 degrees, they're way different, like 21,000 or 2,108 miles compared to 1,466 miles. So that's why I think there's that sort of issue with people saying that the distance calculator using the curvature calculation doesn't work. And what I figured out was that it's not actually meant. The problem is that we're putting in a curvature, we're putting in a value of curve, which you see over here in this diagram, when the curvature value is not, what it's measuring is this value, is the hypotenuse. So it's taking two separate values, the length, sorry, the length, or the height and the length here, right? And that's basically, and if you use those two values instead of the curvature, then the values match. You get a proper, these numbers work, but the distance is going to be a little different because it's a hypotenuse distance, not a curvature value. And again, I put that in my post, and you can take a look. I also wanted to put in the ball earth math numbers so that people could compare sort of these values, especially I think I took it to about 100 miles. So if you look at the numbers here, I wanted to match those up with these numbers so that people could actually see that they're the same values. And if you look right about, get these out of the way here. Sorry. These are what I'm trying to say. So if you look at, let's see, the 1.26 here and the 1.26 here, they're very close, right? They're very similar. Same with the curvature value, but as you get right, around where is it here? 31 here, around 7 degrees, they start really separating out. So by the time you get to 2,000 miles, that's 542 versus 556. And then at around 49 degrees, it's 1466 to 1375, and then it really gets extreme as you get to the higher numbers. And the reason being is that the ball earth math showing you is just measuring these two lines here. So, and it's the same number that if you forced a line along the line of sight from both these directions, as I mentioned, along here, that's what they're measuring. It's just these two lines of sight, and that's not what we're looking for here at all. So once you start getting into higher numbers, because we have to extend this line out so far for it to match the line of sight of the person at the point in my diagram here, A, just like I've shown here. So that's sort of what we're trying to contemplate here. So hopefully that makes more sense. You read the post and let me know if you make some comments and tell me what you think or what we need to do to make it more clear. But hopefully that makes sense, and we can have a really effective way to measure, what we're trying to talk about, which is distance to horizon on a ball. Thanks for watching.